So let's go over and open up what I'm calling lecture 1 here. Again, these should be on the drive, and if you wanted to follow along the slides, so you can flip back or forward, you're welcome to do that. Okay, so the first thing I'd like you to do, while I'm going to be starting up on these slides, I'd like you to call up AnyLogic. You should be able to do so on those computers by going to the Start menu, All Programs, and then choosing under the list of the various programs AnyLogic, and I believe it's AnyLogic University or AnyLogic Educational that's on there. It's University. Okay, and you should be able to click that. And I think I'll follow along just so that we're in the same basic boat. I'm going to have a slightly different version than most of you. I'm using the professional version here. And again, the professional version is available in November, that license key. When it comes up, it's going to be loading a bunch of things here, and you should probably see initially a screen kind of like this. It provides some links and example models and so on. What I'm going to do is I'm going to ask you to go minimize this screen, this button over here. You'll get a chance to look at the basics of the interface here. And when you minimize the screen, you'll see a potentially just sort of disorienting set of windows here. We'll get to understand the function of those windows in a bit. Just ask for your patience while we go to the Help menu and go to Example Models, okay? And we'll see this screen here popping up. How did I do that? Let's try that again. In case anyone didn't catch that, I went to Help, and I went to Example Models, okay? Sometimes it may come down at the bottom of the screen, if so you can click and drag it up. Pre-answer is deployed in awaiting action in the back here, so just raise your hand if you need help, okay? At any point, please indicate, okay? Within this screen here, this example model screen, I'd like you to go click on the how-to models on the left-hand side there. Again, there'll be a set of things shown here, and I'd like you to look at how-to models here, okay, on the left-hand side. And when you do that, a bunch of links should be shown on the right-hand side, and I'd like you to scroll down and select one called SIR Agent-Based. So let me rehearse this for you again. We're going to go Help, Example Models. We're going to click on the How-To Models. And once you've clicked on that, you can go down and you should be able to click on SIR Agent-Based. Okay? So if we click on that, we're going to load in this model. This is one of dozens of models, example models, provided by AnyLogic. I have provided you several dozen additional models which are focused on the health space, which we've built up in my group, to which you have access, and we'll be loading them in later. Right now we're working with AnyLogic sample models. So once this model is loaded, we see a bunch of features of it. So up on the upper left-hand corner, you'll see an indication of the basic structure of the modeling project. So there's a hierarchy of components within this model that are the pieces out of which this model is built. And I'm going to explore with you the meaning of some of these pieces. Broadly speaking, we have a main component that represents sort of the model as a whole, and a set of persons that represent the agents. The agents are going to be circularly going to be strutting within main. Main is going to be their context, and these particular individuals will be interacting within the context of the main class. Person is describing a particular class, and then at the bottom there's an experiment, which can be one of many, that describe different assumptions that you might make with this model and allow you to very easily run those as different experiments. So ladies and gentlemen, I'd like you to go open up the person class. This model depicts a very particular but stylized context. It's a toy model. It's a model for teaching. And it's not a model that tries to speak to a particular epidemiological context or address a specific research question. but it's a model that illustrates many of the mechanisms in the use of the AnyLogic software. So if we click on person, what we see is a depiction of a person as traversing through through a natural history of infection with respect to some pathogen. Now, in this case, we're characterizing a model that relates to the spread of a pathogen in population, but we can imagine this model as speaking to other cases where contagion is taking place, where there's a spread from person to person of an idea or meme or belief or behavior or attitude spread by imitative behavior, passing on a rumor or what have you. So within this context, we have people starting as susceptible. Through a certain process, they are infected with an idea or with this pathogen, and after a certain period of time, they recover from that infection. Their progression through these states is governed by factors that aren't immediately visible here, but are clear once we end up clicking on some of these elements. So, for example, an infection occurs here upon the receipt of something mysterious called a message. By contrast, a recovery occurs with a certain rate, a certain chance per unit time that they'll recover, regardless of how long they've been infected. And, in fact, within each agent's infected state, they can spread the infection. They can send an infection to a random neighbor, for example, with a certain chance. Now, these agents are going to circulate in a large space, and they are going to be situated within the space such that they have 4 neighbors, one in each cardinal direction, north, south, east, and west. And reflecting that physical proximity, it's to those neighbors that they can spread the infection. They can sneeze, and someone to their left or to the right, in front of them or behind them, will get infected. So we're going to place these agents in a specific context. And we're going to color them so that their color in that context progresses according to the colors we saw within their state charts. Okay? Just like this. So here's a question for you. What type of behavior would we expect to see from a model like this? So we have these people going through these stages of infection, and they can spread infection to their neighbors north, south, east, and west. What sort of what might we expect to see if we looked visually at the set of all these people laid out in a grid? What might we see? Anyone? Yes.
It turns red, and then after a while it turns gray.
Great. Great. So at an individual level, a given person, assuming they get the bug at some point, they'll go from a yellow state, representing their susceptibility, to an infectious state, to a recovered state. Good enough. There's no mortality transitions here. There's no transitions associated with that would lead them to be persistently infected or lose immunity. What might we see sort of over the course of the space? So for a particular individual, they go through that. How about between individuals in the space? In this case, they will actually sneeze, and when they sneeze, exactly one of their neighbors is going to be infected. But they'll sneeze at a certain rate, certain sneezes per day, as it were. If we go up here, we could see in this model, the time unit of this model is days. We have number of sneezes per day indicated by this rate here. And it actually takes account the infection probability. So it's actually sending a number of infecting sneezes, as it were. So they have a pretty good chance of infecting people here. So what might we see? Well, it's kind of hard to piece all these pieces together. So let's go run this model. So to run it, I'd like you to go right-click on this experiment and do run. Reflecting AnyLogic's general flexibility, you can also run through this menu item up here, or through model run up at the top there. You can kind of pick your technique and do so by right-clicking on this, okay? Now, when we click, we get a screen that's kind of an introductory screen. These screens are an interface to the so-called experiment. We could change assumptions there, and we can set things up. For now, we're just going to press this button, and it will switch over to actually run the model. And this is what we should see, something along these lines. Okay. Now, while this is running, I'd actually like you to go down to the bottom part of this screen and click on this little triangle, this little yellow triangle, and select model time here, okay? And that will actually show the time of the model. Note this, through this button up here on this yellow button, you can pause the model. Pressing this green button again will start it. We could terminate it with the red button. These indicators here, these controls here, toggle between the model running flat out as fast as it can, or a situation where we can selectively adjust the speed of the model. If we want to slow things down, we can do so. We can speed things up by clicking here, make it go a bit faster, or we can run it flat out. Now, I noticed that in my case, that infection reached the top of the screen there at time just over 300. It was time 308. Notice what's come about as a result. We've seen the screen go gray. So let's go run that again. I've just pressed the red button to get us back to the screen. The experiment is terminated, and I'd like to press this button again. And here again, we see the infection spread. Can anyone describe at a qualitative level, what do we see? Why do we see this? So maybe I'll pause the model, again, using this button up here. Can anyone explain at a qualitative level what we see before us?
We're like a puddle spreading.
Okay, puddle spreading, good. So the gray part of the puddle, what does that depict? I had mentioned it earlier, but it's worth emphasizing. Gray indicates people that are recovered. Yellow, people are susceptible, yet to be infected. And red, those who are currently infected and infective, in fact. They can spread the infection as well. They're kind of one and the same with respect to this model. And we can dive down, ladies and gentlemen, using an interface up here. It's actually not selected by default, but we can go and we could say model navigation. I'm trying to teach you some life skills in this process, how to maneuver around these models. You click on this button here, this yellow button, you go down and click model navigation, and this allows you to go dive down to the level of a given person. For example, this person is recovered. The second person is susceptible. This is person number 1 in the population. That other one is person 0, person 1, person 2, person 3. You could see different people or different states, and you see their colors actually indicated here. This one's gold. This one's the next one down is in a gold state as well. This one is in a gray state, etc. Okay. So here, particular people. Those people are situated within this broader context. So we see recovered people. We see susceptible out here in red on the sort of this boundary. Could anyone describe at a qualitative level sort of what's going on here? Why do we see this kind of odd semicircular shape? Why do we see this arc across the model? And why is it moving? Anyone? Does anyone need TA help so they could see this themselves? No? Okay, why is it we see this, though? What lies behind this sort of pattern at an intuitive level?
Individuals who've once been affected don't get reinfected.
Ah, okay. Here, key element. So they don't get reinfected. Okay, so that's a good piece of the puzzle. And so what's going on here? And because of that, the infection is, among other things, spreading outwards into the susceptibles and not spreading back. So you see this sort of border, this ring of fire spreading outwards into the susceptibles, sort of like an unburnt prairie. This is kind of burnt prairie. You see it spreading out there. It can infect the people on the periphery only. We have some people who are still infected in the interior, but that's because they got infected a while back and they just haven't recovered yet. They have a certain chance per day of being sick, and they've got that nasty flu where they're sick for 2 weeks straight. But for the most part, the people who were infected a long time ago are now recovered. Those people in the periphery are still infected, and these people susceptible have yet to be infected, right? And it's spreading out from there. So that's good. Now, let me ask this, folks. Let's take a look at this. Now, this ring we see, and this, it's gray in here, yellow out there, with the red in the middle. Where is that in the model? So where does it say to produce the ring? Is it here? Is there something about a ring here? A ring there? Where's this ring? Where's the fact that, we have a gray center on the interior and a yellow on the outside? Is it somewhere in this model?
I give you the permission to phone call to anyway.
Okay, where is that ring? Yeah.
It's dependent on the contact between the infected.
Good. That's right. It's dependent on the contact and the nature of that contact, that they contact their neighbors north, south, east, and west. It's dependent on their state transitions, their natural history of infection as depicted by the model. The model kind of depicts a theory as to how the world works, and this is kind of characterizing, this model's particularly stylistic sort of representation of the world. And surely that ring depends on this, the fact that people, once recovered, never can get infected again, and they go through an infected state before recovering. So that's reflected in that as well. In short, this pattern that we see is an emergent property of the model. It's in no one place. In no one place does it say impose a ring that is gray inside and yellow outside and has a red border that matches this sort of formula for the ring shape and where it is located. It's an emergent property of this model. Notably, folks, if we run this model, for those of you who are from system dynamics background, for example, where we're dealing with reference modes that have to do with, counts of people in different states, we could keep track of the number of people, say, who are susceptible over time and show a graph of that, the number of people who are infected over time and show a graph of that. And that would be great, and we'll see how we can do that quite easily. But it's notable that we also have a sort of reference mode that's spatial. There's a pattern that's associated with this model not only over time with respect to the count of people matching certain characteristics, but over space as well. And that's a notable feature. But let's take this model and now let's make some changed assumptions. We just ran it with some default assumptions, and I'd like to work with you to introduce alternative assumptions, okay? So what I'd like to do is we're going to use this to kind of explore our understanding of how AnyLogic works and the AnyLogic vocabulary. So the first thing I'd like you to do is to learn a little bit about experiments. So let's go add some experiments that investigate various counterfactual situations. Maybe this is kind of the base case, this experiment here, sort of the default case. Let's create some alternative experiments. I'd like to actually create them with different assumptions. So this would be an experiment with I should go highlight. If we go look at an experiment, you'll notice that when we see the experiments describe the assumptions to use for a model. You'll notice that this experiment has some assumptions in place for average illness duration, for the contact rate, for the infection probability, and for the total population size. Those assumptions are associated with so-called parameters in this model, and those parameters are associated with the so-called main class of the model, the place where these things are encoded. So if we go up to main, we double-click on it, we see a window pop up that shows you the main class. And you'll see, if we scroll over to the left, a set of parameters. Those parameters communicate assumptions from the point where they're created from where that's created to where it's being used. In this case, it's the experiment that specifies what to assume about those things. In this case, there's a average illness duration of 15, a contact rate of 1 person per day, etc., an infection probability. So ladies and gentlemen, I'd like to create counterfactual assumptions. Let's run an experiment with different assumptions. So to do this, let's modify this model. So right-click on the model as a whole and do New and Experiment. Okay? And I'd like you to type long duration of infection, okay? So how did I do that? Again, I did it by right-clicking here, did new, and then did experiment. And I said long duration of infection. And this is just a standard simulation. You see, AnyLogic allows us to create many such simulations. For now, we're just going to create that one. Long duration of infection. We're going to make this have an infection duration of 50, 50, not 15, but 50. So I encoded this changed assumption down here in the parameters area. So each experiment will run the model with different assumptions in place, typically. And I'm going to make it assume a longer duration of infection. What is that really meaning? How does that unpack? Well, let's go look at person here. That relates to how long it takes them to recover, to go from infectious to recovered. You notice that that's based on this thing, average illness duration. This is referring to the parameter value which lives in Maine. Okay, so this new experiment, we've had an average illness duration of 50. Now I'd like to add some more experiments. Let's have an average illness duration that's shorter. Okay, let's have an average illness duration. Let's have shorter infection duration. These are not particularly elegant names. And we're going to assume an average illness duration of 10 for that. And then finally, we're going to have a one called brief infection duration with an average illness duration of 5. Okay? These are different counterfactual situations. It's notable that here we're making an assumption about something about the natural history of infection, but this might relate to policy at a certain level. For example, the fact that we have a shorter illness duration may be a sign that our healthcare system is more successful in locating people quickly. We're finding them more quickly through contact tracing. We're undertaking interventions which bring down the average amount of time people are circulating sick. Maybe we're able to process them more quickly in a healthcare setting, and therefore are able to give them a more effective drug cocktail, which brings down the duration of their illness. So while we may be changing parameter values here, they could be reflective of policy change in some cases as well. Okay, so ladies and gentlemen, let's take those runs, and now let's go to run them. But before we do that, I'd like to raise the question, how do you think having a longer duration of infection would affect things? Anyone? So if we had a longer duration of infection, how would that affect what we've just seen? So we have the infection spread, and it's spread in about 310 time units out to the end of the boundary, to the top boundary. How would it affect things here? Broader red thing, and the boundary will get to the boundary quicker. So I hear some good ideas. After all, if people stay infected for longer, we'd expect that border to be thicker. They stay infected longer, so the border gets further along before they recover, so there'll be a thicker kind of edge of that border. Second level, in terms of infecting people, well, if people stay infected for longer, you might think, well, they're going to be circulating longer. They might infect more people over the course of their illness, and it might mean the infection will spread more quickly. And indeed, from some models, we might see outputs like that, particularly certain aggregate models. We might. Now, let's go run this thing now. Right-clicking on this. Let's build up our AnyLogic muscle by right-clicking on this and executed this. And you'll notice that we're starting to see infection spread. I noticed that there's a red indication down here, which means it's somewhat short of memory. It will still run, and I'm going to speed this up as fast as I can. It'll still run, but it's going to run kind of on the slow side. So I'm going to actually give it a little bit of a benefit here. Oh, in this case, okay, it's taking a while to actually update. it's really working at it. Let's go see how we could speed this up a little bit. So ladies and gentlemen, for this long duration infection, click there. Let's give it a bit more memory. It was telling us, help, I need memory. It's like we need to feed it some food. So you click on that long duration infection, click on maximum available memory, and change it to 1024. That will really make things go a lot faster. It would have been okay, but we wouldn't have seen it as clearly. How did I do that? I went to the experiment, and then I clicked on maximum available memory and changed it to 1024 rather than 256. Do you see that? Okay. And there's a technical reason for what's going on. It's associated with it sending more messages. And now let's run this experiment as fast as we can. You notice I put on this button here, and it's spreading out here. And I'm going to time this once again. It's time 100 and spreading out here. And we indeed see a thicker border, just as Steve prognosticated. It actually seems to be taking longer, and it actually is running slower. Notice by giving it more memory, we cleared up that issue down there. And it's running out here, and it's going to take some time to reach the border. Let me ask this while we're pondering this. So we see on the edge of this, it's not quite a perfect semicircle. There's irregularities here. Anyone want to guess as to why? What does that indicate? This is irregular. It's not perfectly smooth. Anyone want to hazard a guess as to why?
The direction that we're infecting is being chosen randomly.
Randomly. What else is being chosen randomly? Well, how quickly people recover. If we go back, I'll switch back to that. But how quickly people recover. If we go back, it's a rate. It's a certain chance per unit time they'll recover. They get a certain kick of the can every day to recover. It's actually continuous. It's continuous time, but they're getting a certain chance per day of recovering. Some people take longer to recover, hence these ones way in here that are still red. Some people recover more quickly. So it's about time 305 or so. It didn't seem to get to the border that much quicker, even though we're infecting more. Seems you're infected longer. Shouldn't it be you're infecting more people? Why not? Why wouldn't it get to the border that much quicker? Well, contact rate is still 1, and there's only so many people you can infect. It's the people right around you. You're every day you're sending a message to infect someone on average, and so here it sort of maxes out. It saturates how many people you can infect. Pretty much everyone's getting infected. Okay, now let's go look at the shorter duration infection, shorter infection duration. What would you expect for that? If the infection duration is shorter, how would that be different? Anyone? Red border is going to be smaller. Let me press that again. So here we go, and this guy here is going to go, and this guy also seems a little bit starved for memory. Man, we should have really boosted it for all of them. Let's go do that. Let's go for this guy, boost it up to 1024, and then the brief one will boost to 1024. That was something which I didn't anticipate would be needed. But now that I look at it, the original one was 1024 as well. Okay, so for shorter infection duration, let's run that, and this is what we see. This will make it a little bit easier to see. Okay, so we have a thin border here, but broadly it's a pretty similar picture at a qualitative level. It's a little bit more irregularities concerning this border. Some people recover before they infect all their neighbors, for example. So we get a little bit of a darker border there, but still qualitatively pretty similar. It actually goes a little bit faster. How about this brief infection duration? Notice I changed the available memory to that, to 1024. And let's go run that. Okay? So let's run it. And what we should see is a very brief situation. Some people in here are still in fact susceptible. Why is that? How could there be some people who are susceptible in there? Yeah. Yeah, there's some people who recover so quickly they don't infect all their neighbors. And once again, we get a very rapid transmission. And there are some people, not everyone's infected anymore. Some people stay unafflicted. The attack rate is no longer 100% for those who work in infectious disease epidemiology or mathematical epidemiology. Okay, so that's good. But here we've been modifying the model as a matter of degree in terms of our assumptions about these parameters. An important principle of dynamic modeling, articulated most strongly within the system dynamics community, is that structure determines behavior. It's the structure of a model in terms of its sort of underlying mechanisms, in this case the states and their transitions to one another, that determines the behavior in a most profound way. Let's go modify that structure of the model. Here we're not going to be just adding an experiment that changes the assumptions. We're going to be changing the structure of the model by adding a transition. So ladies and gentlemen, I'd like you to go over here in the projects window and click on this thing called palette. If any of you don't see it, you can get it to show by doing View, Palette. And in general, in this interface, again, trying to teach you life skills here, you go up to View and you can click on this and it will end up showing the palette as a window. You can enable or disable windows here, okay? And you can drag them around by sort of dragging on the tab here, which is useful. Sometimes you want to put them in a different place, but I'm going to keep these here. Okay, so let's go look at the palette, and let's go down to, we're going to be using the palette a lot in the courses bootcamp. Let's go down to this thing that says state chart. It's about 6 down, and it has a little thing going into a little yellow box, okay? And I'd like you to drag in a transition such that it goes from recovered state there, okay? Now, if you drag it somewhere else and it's not quite right, you can always pick it up, click on it, and drag it over. Ladies and gentlemen, please be sure that the sort of little handle at the end of it turns green when you drag it to indicate that it's properly connected. If it's nearby but it's not green, it won't be connected. You have to actually drag it there. So it's going from recovered, ladies and gentlemen, up to susceptible, okay? And I'd like to suggest that you just put it to susceptible without worrying about the location too much. And then we are going to improve its aesthetics, we're going to double click on it and drag it here so that we can actually see the transition go in a more aesthetically pleasing way. In general, you can sort of reroute these transitions by double clicking on them and dragging up like that. And so we can sort of arrange these as to our liking aesthetically. This is not changing the semantic. It's not changing the meaning of the transition. It's just a matter of aesthetics. So I double-clicked on this, and then you can drag it. Double-clicked here, you can drag it. Okay? Note, ladies and gentlemen, that people have a green transition here and here. There should be green to indicate it's properly connected. So, again, big picture, for those who may have gotten lost. Those who may have, if anyone got lost, the first thing I went to the palette. If necessary, you can make it show by the View menu. It'll show the palette. I then went down to this thing here saying State Chart. Selected that. I then dragged in from here over to this window and arranged it so it went from recovered to susceptible. Okay? Now, anyone need TA help here? TA help? Okay? Okay. So, conceptually, folks, what does this transition represent? If we're going from a recovered state to a susceptible state, what does that represent? A loss of immunity, a waning of immunity. So let's call that, let's name that transition, call it waning immunity. Okay? Waning immunity. And I'd like now to, how do we do that? How do we do that? Well, again, life skill. You click on the thing and it should say in Properties window, it should give the attributes of that transition. See, the fact you've clicked on this transition here allows this properties window to come up. I might point out, folks, that you can also select things up here in this window over here in the projects window. You could also select that same transition down here and see it come up. So you can select it either the canvas, this thing at the top, or over here in the projects window. So I called it waning immunity, and then let's do show name so that it actually shows the name next to it, okay? Okay, waning immunity, and drag it over here, okay, waning immunity. I'd like to make this a timeout transition with a time of 150 days, okay? What that means is someone's going to maintain immunity to this bug for about 150 days, about half a year. Think flu in the context of rapid flu mutation before they transition back to the susceptible state. That loss of immunity might reflect evolution on the pattern of the bug. It might reflect changing T-cell complements within our body. It might reflect decreasing antibodies. We're abstracting over that. We're just saying people's hiding the details associated with that, but people's immunity wanes after exactly 150 days, 150 time units, where the time unit of the model, as you could see from the model itself, is day. Okay? Okay, so we've imposed this waning of immunity. People lose their immunity after exactly 50 days, 150 days. I would distinguish that from this earlier transition where we had a kick of the can, a certain chance of recovery per day. Here you're losing after exactly. These are two different types of transitions. There's a third one associated with infection. Okay, so ladies and gentlemen, we've just changed the structure of the model. How do you expect it will change things? How would the model's behavior differ now? Anyone? Ah, okay. So there's going to be a resurgence of yellow. There's going to be an infection spread, but the yellow is going to return. Okay. Anyone else? Sorry? Concentric fringes, because you might have the potential. Maybe those yellows, some of them will get infected, in which case you have another outbreak. Okay. Okay. Let's run it. We as humans are not very good at reasoning through these things totally consistency. Computers are very, very dumb in general, but there's some things they can do well, very mechanical tasks, routine tasks, and that's where they can really shine. And one of them is solving a model like this, actually saying moment by moment what's going on in the model like this. So let's go run the baseline scenario. We'll go right-click in the simulation thing that says simulation. Let's run that. Now we're running the same experiments as we did before, but it's with a different model. It's with a different theory as to how the world works, a different dynamic hypothesis. So let's go run. Do you see anything different right now? Huh? No, I don't see it. Oh, you see something different now? Okay. Okay. What's going to start happening there? Okay, concentric circles. Now we see sort of a secondary outbreak. Here's the original outbreak still going on. Here's a subsequent outbreak. Oh, and here's some sort of tertiary, quaternary outbreaks, and so on. This is with the default assumptions in place about sort of recovery time. Okay. We still got some residual susceptibles in here, and here we have another outbreak coming, and you get another wave of infection. Okay. Structure determines behavior, folks. We've seen a very qualitative difference in the behavior of this model, reflecting the change in the structure we just imposed. That one transition made a very material difference in terms of the dynamics of this model. Dynamics is illustrated in terms of the time series of the number of people infectious, for example, but also in terms of the spatial dynamics. We see something very different phenomenologically from this model than we did originally. But let's go run our different scenarios. Okay, so let's go run a scenario that involves a longer duration of infection. Okay, so how did I do that? How do I run it again? I again right-click on it, or I can select it, and I can go up to here and do long duration of infection. Okay, so here we go. Again, I'm running this thing flat out, as indicated by this button here. And how is what we're going to see? Anyone want to predict what's going on differently now? What's going to happen? Great, great, exactly right. So here's the countdown has begun, right? We're at 121. There's still plenty of reds around. Still plenty of these residual infectives from the previous generation. We're counting down, and what's going to happen? What's the magic number we're waiting to? 150, because that's the time the first of the earlier wave might start recovering. And there we go. Maybe you can't see it, but I can. This is a new wave, but you don't really see these totally distinct waves, right? I mean, it's there, but it's kind of intermixed, interplayed with this here. Okay, ladies and gentlemen, let's go close that out. Let's go try the shorter duration of infection. Anyone? How about a shorter duration of infection? Shorter from baseline. Anyone? TA help? Anyone? Running a shorter. So I'm running these same experiments with different assumptions, but for this different model. Okay, now that's interesting. It's starting out here. Oh, I'm not running it at full speed. It was starting out very slow. I'm not running it at full speed here. And here it's spreading out. Okay. So now we're getting this new wave spreading out. Anyone want to hazard a guess what we might see? That's a pretty big difference there. Notice it now says time infinity. There ain't no work left to do. There's nobody infected, so no one's going to be changing. Smart enough to know that. There's no one infected. There's nothing that can change people from the other states that are in, recovered or susceptible, and at a technical level, there's no events to handle. Okay, how about a very brief duration of infection? Very, very brief, like 5. Well, once again, we're gonna get this spread, and it's not going to lead. Very likely, it won't lead to any subsequent, and so it'll turn all yellow, and that's it. Boom, done. One thing that some of you might have encountered, just by the luck of the draw, depending on when you click things, in some of these cases with a very brief infection, you actually get no outbreak at all. The outbreak never happens. How could that be? Well, just by the luck of the draw, the person recovered before they could spread the infection, and there he goes. I just ran that. Nothing happened at all. By chance, there was no outbreak. That person, that index case, that very first case of infection, recovered before they could infect anyone. By the luck of the draw, they didn't get that message off to their neighbors. They recovered, and there's no outbreak at all. So we've seen this model. We've seen that it illustrates a couple of principles at different levels. One of them is it illustrates that this general sort of phenomenon, in fact, motivation for age-based modeling and in system science models more general, of emergence. We could see very, very different behavior from a system as a whole than we do from its pieces. The whole is greater than the sum of the parts. The behavior of the entire system, ladies and gentlemen, is very different from the behavior of any one component of its pieces. It's not the sum of the components and pieces or the average. It's distinctive. It's in some sense surprising. We can't exactly anticipate it. And it's not in any way presupposed by the model. That expanding ring, the fact it's gray inside and red and yellow on the outside, it was in no way directly encoded or presupposed or fixed in this model. So at a certain level, it gives some indications of principles of system science, the fact of emergence, and the fact that structure determines behavior, etc. Secondly, I hope it's giving you some indication of the AnyLogic interface. AnyLogic is a package which, better than any other agent-based modeling package in the market today, allows you, or available open source today, allows you to characterize a model's basic assumptions, its structure, and its dynamics in a fashion that specifies the what of what you're capturing and less so on the how. So here we sort of characterize what we want to assume about this model, saying let this recovery take place with a certain rate, and it figures out how. You're not writing for loops to say, okay, is this agent going this time step or that one? It's taking care of figuring out drawing from the requisite exponential distributions, etc. And we can sketch that model out in a way that's actually capable of being communicated to stakeholders. We could take a diagram like this, go to someone you're working with and say, what am I missing? Is this basically capturing the situation? And they can relate to it to a degree. It provides you with a way of making assumptions about the model in a transparent fashion where the parameter values are clearly described, where you can easily rerun those experiments, and allows a ready means of graphically describing the model, characterizing its dynamics over time. So here we have this model. It's a model that is toy. It's not like some of the models I provided you, which are more serious research, which represent more serious research investments, or others that I could share with you privately of the same sort. But it illustrates some of the basic features we're going to be encountering in the course of this boot camp and working with. You'll also recognize that there's a lot going on there. And in fact, I'm going to be talking in a little bit about some of the elements of the agent-based modeling vocabulary, because it's distinguished as a vocabulary compared to, say, system dynamics in terms of the richness of the primitives that it uses to build up a model. Whereas system dynamics has stocks and flows and sort of elaborates things a little bit with auxiliary variables and so on, it has a small vocabulary and can do very, very powerful things with that. By contrast, we have in agent-based modeling a much larger vocabulary and a rich set of primitives to work with, and correspondingly more investment to kind of learn how these pieces fit together. So this was sort of our first little encounter with AnyLogic. Any questions that I can address before we go on to the next thing? Yes?
I wondered how they got infections, or that like something.
Okay, so we'll go and see that. Remind me of your name. Shadi? Okay, so Shadi asked, how did people get infected? You know, we have sort of a chicken and egg situation here. Infectives infect, susceptible, which becomes a new infective, but where did that original infection come from? Where was the original infection? Okay, let's go check that out. Let's go up to main, double click on main, and we'll go and see that in the on startup area of main, what this is telling us is that when this whole model starts, we should send a message, which basically is a means of communicating with an agent, saying, do this, sending some information to them. It sends a message that says infection, and it's delivering it to a randomly chosen agent within this main. So main represents sort of the stage in which the agents move around. It's a set of all agents, their environment, their sort of context, and it's delivering this message to a random agent. And by delivering that message, we see that we can go, if we double click on person, we see that it's that message, that receipt of this message, that leads a person to go from being susceptible, to being infectious. When they get a message, they go from here to here. So it's that first message which kicks it off, and then once people are infectious, they send messages to a random person. Does that make sense? Okay. Any other questions? Great question. Yes, Maria.
Nobody else has it, but when I'm running it, sometimes where the time stamp is, there's a little red explanation.
Yep. So that's an indication of something that's going on in the underlying engine for AnyLogic solving the model. It's not an indication you have to worry about a lot, but at a technical level, it indicates a certain situation, and I think it may be, I'd have to go back and double check this, but I think it may be something having to do with two messages going off at the same time or something like that. But I'd have to go double check that. And there's ways that you can specify how to handle this a case of this is so forgive me for going down to this level, but AnyLogic is actually running in continuous time. What that means is most agent-based modeling platforms out there by default, say NetLogo is an example, repassed over most of its time, Swarm, SDML, they tend to run in a lockstep way. You're going from time step to time step to time step and fixed time steps. Tick 1, 2, 3, 4, if anyone's worked with NetLogo, you have these ticks. And here, we don't see that. Here it's a continuous time framework. AnyLogic is similar to, for example, ModGen and other microsimulation frameworks in the sense that time is handled continuously. So you can have things going on as fine-grained as needed. And sometimes things go on at the same time, which sometimes requires subtlety in deciding how to handle them. And it may have to flag that, but I'd have to go look up exactly what that means. But it's something that is sometimes a helpful thing for figuring out what's going on in the model, but it's not something of great concern. Okay, other questions? Yeah. And remind me your name?
Laura.
Laura, thank you. Okay. Okay. Yeah. I think that's that issue with the event handling. Yep.
I noticed in the experiment setup in the randomness section, that what you're talking about, selecting.
That's right. That's right. Yeah. I'm gonna have to go back and review that. It's this one right here. Yeah. I'll double check on the technical underpinning for the meaning of that. Other questions? Yes. Sid.
Where can I see the topology of where agents infect each other?
Okay, sure. Great question. So how is it? So I asked you to take it on faith that agents. In fact, the other agents, the north, south, east, and west. Where is that specified? Let's go to main. Here, like most things in AnyLogic, that's specified graphically, or through a graphical interface. Let's go to main and scroll down, and you'll see that down. So in the main class, we actually specify, and this is a difference from version 6, incidentally, where we have explicit environments. Now, every agent provides an environment for any agents within it. You scroll down, there's a thing that says environment for other agents. And specifically, you'll see that there's a neighborhood type, more neighborhood. There's two types of neighborhoods, more and Euclidean, okay? And those specify whether you're surrounded by 8 or by 4 neighbors, okay? So in this case, you could specify, who do you consider my neighbors? The ones on 4 sides of me, or the ones on 8 sides of me? Is that helpful? I think actually Euclidean is 4 and more is 8, if I'm not mistaken. I have to double check that, but I think this is actually 8 as implemented here. Okay. Other questions? Good question. This is where it says the agents are arranged in a grid. Here we have this. It's up in main. It specifies a lot of the sort of key things. Here are the people, the total population size, for example. Is that helpful? Okay. Okay. Very good. So I think with your leave, then I'll close this model, and we will go on to the next topic.